Hello, everybody. Welcome to our third day. Thank God it's Friday of Beam College. We have lots of content for you. We've been advancing on the complexity of the scenarios that we've been talking about, and today we'll start our first session of the day with Emily Ye, who will talk to us about custom containers in Beam. So, Emily, it's a pleasure to have you. Please.
Yeah. Hi, everyone. Good morning. So I'll be talking about custom containers in Beam today, which is a new-ish feature to provide your own SDK harness container image in a portable pipeline. Now, maybe you know what that is already because you've been watching Beam College, but if you don't, we'll quickly go over that. So you've probably seen this slide in many forms during this uh, Beam College, but a quick overview of Beam portability is you write a pipeline in any language of your choice, and then Beam takes it and translates it into a form that any runner can understand. Um, and so we have several different SDKs per language and several different types of execution engines or runners that orchestrate the actual running of your pipeline. Um, but today we'll be talking a little less about the building blocks of the pipeline or how to make a pipeline and more about the pipeline execution itself, aka the worker or worker environment that your code runs in. And so this is sort of the basic outline of a pipeline. You, using the SDK client, write your pipeline and you submit it. And through the job service, it gets submitted to a runner, which handles the details about how workers are spun up or anything like that. You know, for data flow, this is obviously distributed workers running in Google Cloud with Flink and Spark and other runners like this. You know, these workers are from a worker pool you manage or things like that. And so anytime it needs to, this runner needs to run your user code in your pipeline in some language, it delegates to a process called the SDK harness. And so this SDK harness is a containerized process that runs usually, that runs user code in your language. Typically, it's in the past been for one language, but with things like cross language, you know, there could be an arbitrary language, and your runners and workers could also only be understanding one language and sort of delegate understanding parts of your pipeline in another language to the SDK harness. And so the nice thing about this is that because it's typically run as a container, um, all of your code and dependencies are packaged into an image, and the SDK is also packaged in there per language. And so this is an isolated hermetic environment that can be spun up in many different ways to just run your code. And so it has or installs the things needed to run this code, namely language, Python or Java, for example, the Beam SDK in that language so that it can take pieces of your pipeline and translate that into things that it knows how to run, and then the dependencies that your code relies on. And so there's a design doc written a while back about this actual container contract. So if you want to read it, you can, but it's definitely not necessary for your understanding of how this works. Yeah, and so we released default SDK harnesses to Docker Hub. These are also cloned to GCR for data flow. And so these contain the basic requirements, dependencies per language. And typically what happens is when users need more dependencies, like their own code has specific dependencies, they either package it into their jar, like in Java, or in Python, you provide a list of PyPy dependencies or setup py, things like that. And we go ahead and run that using pip. And so this is how we typically install dependencies. But if you want sort of like more control over that, there's not a lot of options. And so this is especially hard with remote runners where you don't typically control the machines being used to run your pipeline. And local running is less of a concern, obviously, because you control that machine. And we also typically include some dependencies on this image that users are more likely to use to save time, like TensorFlow, but only specific versions of it. So typically, if you're using a newer version of TensorFlow or things like that, you have to download it. And so the custom container, this is like where custom containers comes in. It allows you to build your own container image to configure the SDK runtime environment and provide it as a pipeline option. And so this allows you to do things like stage any sort of file you want or any large dependencies that you don't want to download all the time. It allows you to run additional setup scripts or installation, and it allows you to do things like set environment variables or just in general configure your environment. And you provide it as a pipeline option. Dataflow right now, this is considered an in preview feature. So there are still some things being worked out around like official flags and things like that. And currently only being supported for Python portable pipelines, which is where this really shines because of how Python dependencies are provided. Yeah. And so there's a link to the documentation if you want to reference this for later. But for now, we'll just talk about the basics of custom containers, aka how to build the image, and then how to actually run a pipeline using that image. Yeah, and so pretty much I'll be using Docker, but if you have some other way of building containers, by all means. We'll be talking a little more about what you need in your image and less about how to build a container image. As I'm sure you know, there is plenty of documentation about that on the internet. But yeah, so there are a couple options for building an image that the worker and the SDK harness that work as a worker SDK harness. So the first option is that you base it off an existing image and then you add things if needed. And so this example shows using the default images that we released to GCR or Beam. So this is using the Beam Python SDK image. I realize there's actually a period missing there. It's supposed to be 3.7. But yeah, this is using the 2.27 image because that's when I wrote this presentation. But you can change this to be any version you need. And so, you know, you can do things like copy in files or set an environment variable. You can run apt-get or any sort of installation you need. You can run arbitrary scripts here. Sorry, my neighbor's dog. And then, you know, you just use Docker build to actually build this image. And so this is like sort of the most basic thing, which is essentially using the existing default images and just adding a couple things on top. Sort of a variant on this is what we call a multi-stage build, which is maybe you want more control over your image. Maybe you already have a pre-existing image and you just want it to be able to be used as an SDK harness image. And so this sort of describes using two different images as base images. So for example, let's say you have my base image as your own image, holding for dog, maybe. Yeah, and so this basically actually installs Apache Beam SDK, and then it copies from the existing default image for Beam Python 3.6 SDK version 2.28, and it copies over all of the dependencies that already exist on that image. Yeah. And then finally, what it does is it sets the entry point to the Apache Beam SDK launcher. The entry point is basically what actually launches the container process. So this is what actually needs to run, and it's probably the most essential part of the image. And it basically actually runs the SDK process. And so last option here, obviously, Beam is open source. So all of this code is like the Docker files and all of our code is open source. So you are always welcome to check out a stable branch of Beam, edit the Docker file. There's the link to the Python one here, but we also have some for the other language SDKs. And then you just build the image using Gradle, which is our build system. I obviously don't recommend this if you aren't willing to get into the nitty-gritty of Beam development. The development environment is a lot to set up because there are so many languages. But if there is something that you really want to do, like for example, our entry point is a Go binary that we release or we build and release specifically only for one sort of OS. So if you really need, a different build of that Go binary, for example, this is where you might want to check out and build it from source. Yeah, and so the important bits of all of this is that your language has, or your image has the base language. So for example, Python has the SDK requirements. In the default images, this is all in this folder, opt Apache Beam. And so this includes, you also want to install the SDK and all of its required dependencies. And finally, the boot script, which is a Go binary that we also put into opt Apache Beam. And so this handles things like provisioning and artifact initialization. So, downloading any files that you've listed as like files to get and actually launching the SDK or worker process. Yeah. So let's actually talk about how to use this now. The prerequisite here is that you have your runners and workers have Docker installed. Our Beam relies on Docker as a container runtime, and so this is just sort of a requirement that we have for now. For local runners, make sure that your image is loaded or loadable in the Docker daemon, aka it can be pulled. And for remote runner and workers, same thing. Make sure that they can pull this image using Docker. Workers might need credentials for this. For example, with Dataflow, your VMs, the default server's account will need access to the image if you're hosting it, for example, in Google Cloud, in GCR, or things like that. Typically, if it is the same project, you don't actually need to set this up yourself, but if you're doing some cross-project things like that, that's something to be aware about. Yeah, and so Dataflow Runner, this is the example. I'm mostly going to be talking about remote runners just because this is where it's the most useful. Dataflow Runner, you specify that it's a portable pipeline, so that's use runner v2, and then you specify a worker harness container image. We also are switching possibly to using a more accurate term. This is sort of like a non-portable pipeline reference. So this basically says use this SDK harness image, which is some image that you've built and pushed to a remote container registry. Testing locally, pretty much the same, but adding in specific flags for using custom containers. So you specify the environment type, which is you want it to be running using Docker, and then you specify the image as part of environment config. There are a couple of other flags, I think, that have been added recently to specify an image, but that should all be documented on the portable runner, but these will still work. And so Flink and Spark and things that sort of use the same portable environment actually just use the same flags. An important thing to note here is that when you do run it in Docker, currently, and when you are running it on your local Docker, currently this spins up container, and so anything written and anything read has to be on that container file system. We're working on improvements on testing in a local environment, and hopefully we'll be able to do things like allow you to mount local file systems to the container file system and things like that. But for now, just be sort of aware that anything you do output is actually output to the container and thus will disappear when you stop running the container. And vice versa, anything that's an input file, if it's not a remote file, has to be accessed locally on the container. Yeah, so why don't we move on to the demo portion? So I've prepared a quick demo. I'm gonna start with Dataflow. As I mentioned, this is sort of where it shines, I guess. And I'll be going over like a custom image that I'll build and then running it on Dataflow. And then if we have some time, I'll go over what it looks like on the portable runner. So here I have a Docker file. So in this Docker file, we are just using the base image. I'll provide the Beam version as a argument to Docker build. We have an environment variable. I'm going to set it right now to Beam College header. And I'll show you sort of where this appeared later. And then I have a custom package that I wrote that is a useless demo package. And so what this does is it's sort of just built on top of word count, but based on the count of a word, we'll add some sparkles. And then another thing, I wrote a very shoddily written text sync just so that it displays nicely in GCR. That's it. Or sorry, in Google Cloud Storage. And so this is sort of like to represent any sort of custom Python package you might want to write, or any sort of strange dependency that you need to include on your image. Yeah, this is specifically for local testing, but I have a copy of King Lear that we copy into the image. And finally, I'm going to be using GMPY2, which is a sort of just fast math library. And so it requires a couple of specific dependencies. And so typically you would have to do something like run a specific set of PY that called out to apt-get. But with a custom container image, you can just run the dependency install right now. And so this installs that dependency and then installs the preloaded package that I mentioned. Yeah. And then my demo pipeline is essentially word count with extra steps. I also have it logging to info right now. This is mostly for local testing, actually. As I mentioned, outputting to a file that then disappears probably doesn't tell you much about what your pipeline is actually doing, but it's pretty easy to add some logging steps. Yeah, and finally, I have a demo script. This is mostly actually for anyone who wanted to look at the code. I'm going to be working off this hard-coded script just because, just in case like my environment variables weren't working properly during the demo. Let's not
Emily,
anger the demo gods.
sorry, could you zoom in a bit? It's just that
Oh,
the
yeah,
font
yeah.
size is a bit too small.
Yeah.
Yeah, that's enough. That's great. Thank you.
Cool. Yeah. yeah, so yeah, I'm currently in this folder. And so sort of the things that I already did before this, I'm using a virtual environment just because Python. I installed the SDK and I installed my custom library. And so I'm going to build my image. I'm using 2.28 as my version because that's the most recent version. And I'm tagging it, and I'm going to be pushing it to GCR. As you might realize, I work at Google. So yeah, and so this will build. Yeah, and so as this build, we'll sort of talk about what we'll do. After this, I'll push it to GCR, and then I'll run it on Dataflow, and I'll sort of go over how to debug it in Dataflow, just because that's probably the more interesting part of like actually running it on Dataflow. Yeah. I should mention that these images are quite large right now, and this is actually particularly because our base image includes a lot of dependencies so that you don't have to install them right away. And so this includes things like TensorFlow, which is quite large. But as part of this rollout of custom containers, we're thinking of basically reducing the initial size of the image. And so if you need things like TensorFlow, you can use like a image that, like a Uber image, if you would, to borrow from Java terms, that has more of the dependencies, or you can choose to use like a minimal image if you don't really need the dependencies that are built in. Yeah, so we've pushed our image, and let's see. Nope, that's not right. Whoa. I forgot I had to do this. Okay, we're good. Yeah, so I'll go ahead and use this image now in a Dataflow pipeline. So basically, a couple things to note. The input is a remote file just because of Dataflow, and I'm outputting it to a GCS bucket. Same thing with my temp location. Yeah, and so these two are really the important flags here where I'm providing my custom image as the worker harness container image. Yeah, so it looks like it's starting to run. And why don't we go to Dataflow? It's uploading my stuff. So
Emily, in the meantime, sorry to distract you.
Oh yeah.
In the meantime, while that's running, we have a question from Dan asking if you need to specify an entry point in your Docker build.
Yes. Well, if you don't want to override it, and you're using the base image, then no. If you want to override it, then yes. So for example, if you're using a different base image, or if you're building it from scratch or things like that, then you do need to, at the very least, run this Go binary that we've provided as the like long-lasting container process, if that makes sense.
Okay, yes, thank you. Sorry to interrupt.
Oh yeah, no worries. I mean, this is clearly the boring part of the presentation. Oh, I probably could have just done that. Yeah, and so this is our pipeline running. Yeah, and my worker logs, as it runs, it should. Yeah, and so as you can see, if you need to like check on your job during the running of this, you can go ahead and look at things like this. And so it'll show up in the options. Just making sure that it matches. Yeah. So this should start running. Yeah, and we'll sort of, we can actually maybe just in a separate window run the local runner. Yeah, and so in a local runner, pretty much the same thing. Well, that's because I haven't activated my environment. That makes sense. Yeah. Yeah, and so pretty much the same thing. This is essentially running the same thing, but basically it's a good way to test your container to make sure that it can be pulled and run locally. And so this is like not necessarily something that you want to do. Just there's ways to run it using direct runner or things like that, but essentially a way to make sure that your container can be pulled and works relatively well with your pipeline. There are just a couple of like sort of things that you might need to temporarily do for local testing, aka credential access or things like that. Yeah, and it looks like our job is finishing up. Yeah, and so as you can see, this is sort of my debug line that output all of the word counts. And so basically based on whether the number was prime or 1, just added some different Unicode characters. And so the final thing that it did was write to a file. So here's our thing. And so as you can see, did I provide the right tag? Unclear. Oh, I didn't save. Well, in any case, so basically what this does is it uses the environment variable that you've set in the image to provide the header here. And so essentially what that does is it allows you to use you can see that the environmental variable has been set on the container and has been used in our pipeline. And so this obviously is not like something that you might do in production, but for anything that might require environment variable or things like that, you can set it prior in your custom container and it should be fine to use in your pipeline code. Yeah. Yeah, we're actually pretty good on time. I might have spoken a little faster than I thought I would. But yeah, so I'll go back to the presentation right now. Oh, another thing actually before I do that. Before I go back, a good thing to check on if you have issues with your container is just to go into your logs here. And so we have a couple of like metrics set up for things like Docker or Kubelet, and those should tell you if for anything particularly about actually running the container itself. And then worker logs obviously show you things about the worker logs. So that's sort of like if you have trouble with actually debugging your pipeline itself, those are good places to go. Yeah. And so, so things to keep in mind when you do this, make sure that your SDK type and version matches. Typically, it will be fairly obvious if you have a mismatched version of Python or things like that, because it will throw an OS error or something very quickly and stop. Beam SDK versions might not matter as much, mostly if there is like an incompatible change. That might matter. But typically what happens is when you run the SDK using a specific client version, it will make sure that your pipeline is actually running that version. And so it will actually go and download it, which does defeat the purpose a little bit of the custom container in that case, because the SDK takes time to download. Yeah. Another thing is also to make sure that your SDK type actually matches, aka don't use the Python SDK on a Java pipeline or vice versa. Unless you're using cross language, then by all means. But yeah, another sort of thing, so the local runner, as I mentioned, the container behavior is a little weird, just to let you know and to warn you about the behavior there. But all the file systems are local to the container, and it doesn't have the same access to environment variables or things like that. So other options, if you don't want to install Docker, oftentimes Docker has to run as root, so maybe you don't want that. So you can build your image using other things. Some examples are like Kaneko or Google Cloud Build, or whatever cloud provider alternative that you'd like to use. Just basically making sure that you don't have to install Docker on your development machine. And finally, a thing to consider is if you're using Docker Hub to host your images, be aware that anonymous users typically only get 100 pulls per 6 hours. And right now, a lot of our remote runners don't provide the ability to provide like a Docker credential or things like that. And so we're limited to 100 pulls per 6 hours, which might not be an issue, but depending on how big your pipeline is or things like that, it's something to consider. And so sort of the next steps here are adding usability features for simple container builds. So hopefully for simple things like adding new files or just setting one environment variable, something like that, you'll never have to actually touch a Docker file or Docker. We'll just pre-run it for you. And then improvements to local container testing. As I mentioned, there are some things that we can do to actually mount file systems or pass in credentials as needed to Docker. And so, yeah, and then in Dataflow, we're hoping to launch this officially once we nail down the usability and make sure that everything is working great. Yeah, yeah, and so that's my talk. If you need to read more about this, there's the documentation. Feel free, obviously, to get in touch with the Beam community and the Beam development team at that link. Yeah, and so I see that there are some questions lined up already. I'll just move straight into those. When using custom containers, are there any considerations, gotchas, as it relates to GCP IAM policies? So in general, there shouldn't be any new ones. So typically the container image should pretty much work the same. And so it has the ability to use the GCE, I forget exactly what they're called, like implicit credentials, basically, that the GCE VMs have access to. So this is basically the default service account on the VM. And so this is obtained through like via metadata, things like that. And so anything that you can do right now with a pipeline with the default container image should work fine with the custom container image. Um, um, yeah, so in general, basically all this does is replace our default image container image. Oh, sorry. The question is, assuming that throughput-based algorithm auto-scaling algorithm is supported, so when scaling up your container images are used, yes. This is just replacing your image. So essentially right now what we're doing is already providing a default container image, and so this basically replaces that with your image.
Our next question is, do you have a list of base minimal packages, base minimal list of packages for when you're using Python, if you do not need optional stuff like pandas or TensorFlow?
Yeah, it is in Beam. We have like a requirements text, and for the most part, they are all dependencies of Beam, but there is a small list at the end that is the non uh, uh, essential stuff. So that's like pandas, TensorFlow, things like that. And so right now, the best way is just to go to GitHub and look at that list and make sure. You can also and then if you really want to remove them, you could also actually just copy that file from the default image when you're building an image, and then just remove the things that you don't need.
Okay. Another question, when will Java portable pipelines be supported?
So I am not sure of the answer to that. I will probably have to get back to you on that. Do you mean portable pipelines overall, or just with custom containers? I think the portable engine has been enabled in Beam for a while now, and with Dataflow as well. But I'm not sure on the details. But sort of like the idea is that once we go to GA launch with custom containers, we'll be able to support Java as well. On the other hand, Java isn't like Java benefits a little less from this because you still have to download the jar that you provide, and so but it does allow you, I guess, to stage jars and things like that already. But yeah, so I guess I'll say technically I am not sure if you are allowed to use it yet, but it should be supported by the time we go GA. But I don't know necessarily how much Java will benefit as much from it.
Okay. Yeah, and Alexander just confirmed that he meant in custom containers. So yeah, that's right. The answer. I think that's all the questions that we have, Emily.
Yeah.
Thank you so much for your presentation. And remember, everybody, that the slides are available in the repository, and also there's a folder with all the files for the container that Emily demoed. So feel free to run this on your own, and let us know if you have any questions. Emily is in the Slack. You can tag her if you have any other question or follow up. And their next session is in 18 minutes. So you have a bit of a break. Our next session is how to do multi-language pipelines. Actually, our next session is focused on multi-language pipelines by David Sabater. So we'll see you in a bit. Thank you so much, Emily.
Thank you.
Bye.
Hi, welcome again with our next session of BIM College. And now we have with us David Sabater Dinter, David Sabater in Spanish. And David is outbound product manager for data analytics on Google Cloud Platform, where he helps to develop GCP products vision and strategy for the data analytics portfolio. And today he's gonna share with us about multi-language pipelines in BIM. So welcome, David, and please go ahead.
Thank you. Thank you. Hi, everybody. My name is David Sabater, and I'm actually based in the UK. So today I'm going to cover in the next 45 minutes multi-language pipelines. Okay, let's move to the next slide. I'm going to cover 3 sections. So first, I'm going to introduce the BIM portability, which is important in the context of the multi-language support. I'm also going to cover the Dataflow Runner version 2. And then lastly, I'm going to introduce the multi-language support, and actually I'm going to run a quick demo. Okay. So first, let's go with the BIM Vision, right? The BIM Vision provides a comprehensive portability framework for data processing pipelines, right? One that allows you to write your pipeline once in the programming language of your choice, for example, Java or Python or Go or SQL, and then run it in any runner, right? So any engine of your choice. If we see that in perspective of a particular functional action like a sample key, on the one side, we have all the SDKs that we can choose, right? As engineers or as a different type of personas, we'll want to use one of these SDKs typically, right? A Java, Python, Go, or SQL. Actually, within Python as well, you can use data frames, which is a similar API to the Pandas data frame. So that's a new addition as well to the family. Now, the context is that, and that's back to the vision, is that you pick up an SDK, and then you are able to implement one of these logics, like the sample key, and then it will be automatically be able to be executed in any of these runners, right? So that gives you no vendor locking. Obviously, I'm from Google. I will always encourage you to deploy these pipelines in the Dataflow runner because it's a fully managed service, but you will always have the option to run it on any other runner, right? And yeah, that's the point in this one. Now, the challenge here is if you start thinking about, okay, in Java SDK, we have many functionality, right? So every single time that you want to implement that functionality in any of the other SDKs, you need to do the effort to actually implement the kind of the middle layer for each of them. Now, the challenge is we have a lot of functionality enabled already in Java, right? So every time there is a new functionality added in Java, someone also needs to work on the equivalent ones for available on the other SDKs, right? And as you can imagine, as the number of SDKs grows and also the functionality that we are adding, that becomes a bit challenging to actually scale the platform and make sure that all these functionalities available in all the SDKs, right? So that's really why the portability framework is it was actually implemented as well as part of the framework, right? So it's a language agnostic implementation just to have to be able to represent and execute your BIM pipelines, right? It introduces a well-defined language-neutral data structures and protocols between the SDKs and the runners, right? So it's kind of the middle layer that allows you to implement once and then being able to use across SDKs and across runners, which is important as we grow the functionality and also the number of SDKs, right? So apart from that, the interoperability layer is actually called Portability API and enables you to use the language of your choice with the runner of your choice, right? Ensuring that the SDKs and runners can work with each other uniformly. So that is just really giving you that abstracted view. At the same time, because we actually provide Docker containerization, you can actually customize your environment, which is really powerful and actually give you more choices, as Emily mentioned before as well, with the containers. So that's another value that the portability framework brings to BIM, right? So yeah, sorry, I'm just the benefits of the portability are a few, right? So every runner works with every language, right? As I mentioned before. The next one is Containerization allows configurable hermetic worker environment with the containerization. And also you can have multiple language pipelines, which is actually the other section I'm going to cover, right? And it's actually allowing you to run cross-language transforms. I will explain later, and you will see with the demo what we mean by multi-language pipelines and then the cross-language transforms. So basically, is you start with the multi-language pipeline, and then you can double-click on it, and then you will have transforms that you can use that are only available in other languages, right? So SQL transform being an example. And all of this will bring you a faster delivery of new features available in the SDKs, right? Because with portability, every time a new functionality is added to support a language, it will be automatically available to all the others, as I mentioned before. Now let's move to the next section, right? On Dataflow Runner version 2. So I'm introducing that in the context of Dataflow because the demo I'm running and the features I'm showing are related to Dataflow. Now, the important thing here is that Beam portability is available in Flink and Spark as runners, and in Dataflow is only available on Python SDK, right? And I will mention a bit more. I will introduce the context on this section. The use of portability features mentioned earlier, you must use the Dataflow Runner version 2 in GCP, right? And actually, this runner is more efficient and portable, and has an architecture that is based on the Beam portability framework that I just introduced. Also, at the same time, it supports multi-language pipelines and custom containers. Now, as of today, 9th of April of 2021, we support the multi-language only from the Python SDK. And for that, you need to enable that when you submit the job, that's automatically available if it's a streaming job in Python. And you need to have also version greater than, I think, is 2.24 or something like that. So you need to ensure that these things are available from the Python SDK, then you will be able to access the Runner version 2. From the Java SDK, it's still not available, and we are working on it. And hopefully in the next few quarters, we should just have that available in Dataflow. But as I mentioned before, that's specific for GCP Dataflow. All the other runners, they support the Python SDK and the Java SDK as well, right? And there's more information here as well about the support and how to enable the new Dataflow Runner version 2, okay? Okay, that's all with the Runner version 2. And now what I'm gonna do is introduce the actual multi-language transforms, okay? So with language agnostic representation of the pipelines and the possibility of specify the environment of each operation, you are no longer limited to a single language, right? In a given pipeline. So portability makes it possible for you to run multiple languages across multiple SDKs and across multiple runners. So imagine the scenario where, for example, you are a data engineer, and then you are being asked to obviously, let's say your SDK of choice is Java, because that's where you are coding all your logic. And then you are in charge of integrating with Kafka, right? Which is actually the example I'm gonna show. So actually, you implement, you have a Kafka I/O available in Java, so you can apply your specifics to connect to your specific Kafka cluster to do whatever transforms you need to do to actually encode your messages and decode your messages, and then you finish there, right? Now, the challenge is you're not the only persona building that pipeline, right? So this is your little part in the whole pipeline. There is then a data scientist that is actually more comfortable implementing the logic in Python, right? In the Python SDK. Now, the challenge is historically, the way you had to implement that will be, okay, I'm a data engineer, so I will implement my part in Java. And because I cannot actually mix the languages, I will need to somehow transform the events and then push them in a place that another pipeline that is actually running Python SDK will pick up these events and do whatever the data scientist needs to do, right? Now, with the introduction of cross-language transforms and the multi-language support, we can do all that within one pipeline, right? So you don't need to, for example, push things from your Java part into PubSub or Kafka, and then use another pipeline in Python that is picking up from there and applying that logic, right? So all can happen within the same pipeline, which is really powerful, because as different personas, I can actually focus on preparing that Kafka IO section, wrapping that up in a way that the data scientists from the side, when they're building with the Python SDK, can actually grab that Kafka IO that was implemented in Java and use that directly without knowing even how it's implemented. It's all wrapped in a Python class that you can call, instantiate, and configure from the Python SDK, and you can then ingest from there, right? And the beauty of that is, as we explained here, is we have a rich set of IOs, right? As I've discussed, we have Kafka, we have PubSub, we have a bunch of them. And at the same time, we have a mix of libraries that we can bring. For example, let's say the other way around. Let's say that I'm a data engineer and I'm implementing a pipeline in Java. And for example, I need to use TensorFlow Extended, right? TensorFlow Extended is only available in Python. Same story. I will need to push the events in a messaging queue, for example, and then implement another pipeline in Python to extract the events from there and actually compute them with TensorFlow Extended to do transformation of my features and then apply whatever machine learning model I have, right? So that's a challenge. And again, here what we can do with the cross-language, multi-language support is within the same pipeline, I can also mix Python and Java and also the future SDKs, right? So again, to go with an example, and that's actually the demo I'm going to run, you can see here that it's really easy to actually implement that. Let's imagine now I'm the data scientist and I have my data engineer that has created the Kafka IO, and it's all wrapped nicely in a class that I can actually import from my Python SDK. And as you can see here from that code snippet, all I need to do is instantiate my pipeline, and then the first action is actually read from Kafka, right? And then I have some configuration parameters there that I can use that are exposed by that class, on where I specify where are my Kafka brokers, and then what is the topic that I need to read from, right? Again, you can see the amount of lines of codes, and I don't really need to know how the Kafka IO is implemented in Java, right? And again, at the same time, I benefit because I have a really small number of lines of code because of the Python SDK. So again, as a data scientist, I'm happy. And then also the Java data engineer is also happy because she has been able to implement the IO efficiently in the SDK of choice, which is Java, right? Now let's go under the hood. What is going on with that, right? What happens when we mix? We have an SDK, in this case, the Python SDK, and then we're trying to embed stages that are actually in a different SDK, in this case, Java, using the Kafka IO equivalent, right? Under the hood, to make Java transforms available to a Dataflow Python pipeline, the Apache Beam Python SDK starts up a local Java service. That happens on your computer, or in the case of the demo I'm going to run, that happens in the Cloud Shell console, but it's not in the cluster. It actually happens locally, right? And what it's doing is it creates and injects the appropriate Java pipeline fragments into the Python pipeline, right? So as you can see here in the image, that's what we're trying to do. The SDK then downloads and stages the necessary Java dependencies needed to execute these transforms, like together with the Python dependencies, right? Everything in that stage, when, for example, in this example I will run, that it will be submitted to the Dataflow service. So we'll see in the logs that actually we are staging all that in GCS buckets. So that's actually how it happens. The next step then obviously is at runtime, the Dataflow workers will execute the Python part, which is the main part, but at the same time, we'll actually bring all the Java code pieces to be able to be run along the pipeline, right? So in this particular case, it will be the Kafka IO to be able to read data and to write data, okay? That's basically the story here. So now I'm gonna switch to demo. Okay, let me stop sharing this tab and then switch to Okay. Give me a sec. Okay, so you should be seeing now the GitHub repo where there's a bit of description of the steps. As I described, what we are going to do is there is already a Kafka cluster I set up. I will show you from the console, but basically there are multiple ways. You can have a Kafka broker set up locally on your laptop. In my case, what I did is I went to the marketplace in Google Cloud. I instantiated with Deploy Manager a single node with all the things. It's open source, so I'm just paying for that VM that is hosting things, but it's all automated, right? And exposes the broker IP and the port number, so I can actually directly connect. So that's the first thing. And the exercise, what it's doing is very easy. So we have actually a public PubSub topic that is actually gathering, is described here. Yeah, it's actually, you can see here, what is the PubSub topic is doing is capturing all a continuous stream of taxi events, right? So we have location and a number of other things. In this demo, what I'm going to do is I'm going to deploy a pipeline that is going to read from the PubSub topic, okay, that is publicly available, like continuously generating events. So that's quite good for you if you want at any moment test your pipelines. That's actually a topic that you connect to and then start receiving events immediately. That pipeline is going to obviously decode that in the right format and is going to write it into a Kafka topic, okay, in the local Kafka broker I created. And then the same pipeline is going to read from that topic and it's going to actually generate logs to show that it's doing the whole exercise, right? I'm going to show I'm going to submit the job, and probably because it takes a couple of minutes to run, because it's about the time, I will go through the logs and then I will show you how actually is doing the execution, okay? So let me switch to a different tab now. Okay. Cool. So you should be seeing now my console. I need to reconnect here with the shell, the Cloud Shell. As you can see, always Murphy's law in this scenario. So I run it a few times to have some previous simulations, so I can actually show you. But let's try to actually run one, right? Brave on a Friday. It's actually 6:18 here in the UK. Okay, it takes a bit because it's provisioning. The instructions for you to do this exercise, they are all included as well in the repo. Now, I'm not trying to follow with you because you had to set up the Kafka broker, and that takes a bit of time, right? So, but you can try that at home. The instructions tell you to actually do it in a particular way with a set of scripts that are already in the repo, but you can also do it from Marketplace or even install it locally on your laptop. There are multiple ways to have a Kafka broker. Okay, so here I'm gonna start. I have always a cheat sheet here to avoid fat fingers live. So first thing, I set the right Python environment to be able to run with all the Beam dependencies that I previously installed. I initialize a bunch of parameters then. Okay. Basically, I export the GCP project, location for where I'm going to stage all the objects and the artifacts before and while I'm submitting the job, location where I'm going to run it, the name of the job, a number of workers. That number is because that it can be a bit of a backlog as well when we are consuming things. So is to be able to consume this happily. Obviously, I don't want to keep this job running forever because as I write things into Kafka, into my Kafka node, I will probably run out of space at some point in time, right? And the important bit is this one. This is where actually my Kafka broker is sitting. as I mentioned, when I deployed that from the marketplace, that was given to me. I can actually show you that quickly. If I go to, when you deploy something from marketplace and it's based on deploy manager scripts, you can actually go to deploy manager and have a look at your deployments. And we have here Kafka one. And it's all, you see, it's all green, configured, happy days. And it's pointing here, it's telling me this is the actual IP from where I can actually connect to the broker, right? And I can do a quick check here that it's working. Yeah, all is working. So next thing then is actually, I'm going to the right location from the repo that I cloned already. Okay. Then the last step is actually submitting the job. Before I submit the job, let's revisit first the code. Okay, important, because I shared before a small code snippet, but let's analyze a bit the code that I'm gonna submit here. So if I again switch into a different tab, sorry about all these ones in between. It should be this one. Okay, you should be seeing my Cloud Shell editor. Here is just the only file I need to submit. You can see this is a Kafka taxi module and it's a Python module. So basically, I have the typical main section where I'm setting a logger and then I'm capturing some arguments, right? This is the Kafka broker where I'm actually gonna write things that I'm reading from PubSub and then reading them, right? Let's see actually the logic to do that in Python, right? First, this method is getting the events and then creating a nice log for me to see in the console, right? Or any syslog. But the actual pipeline is instantiated here with the options that we provide as we submit the job. And then you can see here, first we do the read from PubSub. This is actually the piece that we are importing, that this is not implemented in Python, right? This is actually a Python wrapper or Kafka IO that is actually implemented in Java, right? So in this case, me as persona, I'm a data scientist in this case, right? All I'm interested is read the events. I know the topic, and then I'm doing some transformation on the events, right? And then all I'm doing, obviously, I'm not going to do too fancy stuff as a data scientist. I'm just writing back to Kafka, and then I'm introducing a window of, I think it's fixed window of 15 seconds, right? Every 15 seconds of events, I'm writing them back to Kafka. So reading from PubSub, mapping, and then writing back to Kafka. And then the next one is actually reading from Kafka, as I mentioned, right? Again, same setup, and then the topic is the same. And all I'm doing is applying a flat map and then applying the method that I just described above to then generate the nice logs, right? So that's basically what I'm doing here with, it's an easy pipeline, but you can see that you can definitely evolve that pipeline and then implement your own logic, okay? So let's go back and then submit that job and see what happens. Okay, so I can go to data flow jobs. Okay, I don't see anything running here. So let me go to my cheat sheet. Okay, and then this is the whole command to run it. Python 3, because the Cloud Shell comes pre-configured with Python 2, so you always need to ensure that you call it Python 3 to avoid problems in case you try using the same method as me with the Cloud Shell. And then obviously the runner is Dataflow Runner, and this is the temporary location where we are staging the artifacts, my project, the region is Central US one, number of workers, and also the name of the job, and important is where my Kafka broker is, right? And the important bit is this one, right? As I mentioned before, I need to run this in the runner version 2, and that is only available in the Python SDK when you run this in Dataflow, right? If you are running, if you were trying to run this in any other runner like Flink, you will be able to actually do the other way around. So you have a Java SDK, So I will do a Maven build or something here, or actually executing directly the Java module. And I will call the Python components, right? Like TensorFlow or whatever we have. But that's not at the moment available in Dataflow. That's available with the other runners. Hopefully in the next few quarters, we'll have that also implemented in our runner version 2. But my point here is that to make that run, we need to ensure that we are using the runner version 2 in Dataflow, right? Only available for Python. Okay, we submit. And you will see that now we will generate a bunch of logs here. Okay, that's basically calling the API service, the Dataflow service, and then we'll start. We're compiling and bringing all the the Java dependencies in this case, the Kafka dependencies. You see, is bringing all these things. Okay, and at some point in time, it will start staging all these objects. Okay. Now it's packing everything and should start any moment pushing. Okay, enterprise. That's when it's pushing to GCS. It's asking me for that. Okay, you see now it's staging everything. Okay, so it's pushing components. Okay, quite a few. Nice. And then after that, if I refresh here, I should be able to see, yeah, okay, I have my new job running here. Nice. So it takes a couple of minutes, but basically it will just take about 2 minutes to start all the workers, 5 workers, as I indicated. You can see that the version I'm using is in Python 3.7 SDK. Is Apache Beam 2.28, right, which is supported in Dataflow, and Central One, as I specified. Now, I will need to wait a couple of minutes to actually see actual results. We can wait anyway because we have time, but you can see here the DAG that we created, right? Basically, what we're doing is, as I described it, we first read from PubSub, right? There is actually a PubSub IO available in Python, so. But we also have what we also need is write into Kafka, right? And we don't have a Kafka IO in Python. What we have is the wrapper that we have the Kafka IO in from the Java SDK, right? So that's the beauty about this. We don't need to re-implement the whole Kafka IO that was already implemented in Java and has been already battle tested. That's another nice feature, because when you introduce new code, obviously you might introduce new bugs, right? So if you can actually use a battle-tested connector that is being used heavily, like the Java, like the Kafka IO, that's a really nice feature, right? So basically, we can see here from the DAG that we are reading from PubSub, we're doing transformation, we're doing the windowing, okay, 15 seconds, and then we write into Kafka. The same pipeline, we have another part of the pipeline, and where we're doing is we read from Kafka, and then we do a flat map and we generate the logs, right? So hopefully at some point in time, I should start seeing events coming through, right? As I mentioned, it takes a few minutes, but at some point in time, I should be able to see a big chunk of events being read from PubSub and being written into Kafka. Okay, let's see. Nothing yet. It's running, but sometimes it takes a bit of time to start refreshing the UI anyway. So hopefully at some point in time, when I click on that stage, which is the one that is generating the logs, we'll start seeing coordinates that they come originally from the taxi trips that we are publishing on the PubSub topic, okay? I'm sorry. Okay. A few more seconds, hopefully. That's the thing about trying things live. It takes a bit of time. Basically, what I will do, obviously now there are not events arriving, but what I will do is I will go, obviously if you were running this in a different runner, you will have to go through the different UI or go in low level and trying to look through the logs, right? Here we have everything from the UI, so I can go here and I can even see the logs that are being generated on that stage, right? At the moment there is nothing, so let's go back. And again, see here, when I was testing events. And then as always, Murphy's Law is waiting a bit of time. Okay. What I can do in the meantime, I will come back to this one, but let's see the other ones that I just ran for a few minutes, right? They should just start at any moment, but just for the benefit of time, I don't want to keep you waiting. I can go here with the one I just ran a couple of hours ago. And if I go here, you see that that's the nice logging that I have that method that is outputting these things. So you see that I was generating them, right? A couple of hours ago, that's local time here. So it's actually working, right? So that's the whole thing here. Let's go back again to this one and see, hopefully now it's generating events. No, it's not. That's always the Murphy's Law. Okay, that's why it's good to have other runs somewhere you've seen the events coming. I promise you that was working. It's just a matter of whenever we get new events. Okay, I think now we should have something. No, not yet. Okay, let's give it another few seconds, and otherwise, what I will do is I will switch back to the deck and then we can finish and then hopefully cover any questions you may have. But as you can see here from the one that I just ran a few hours ago, it was running, it was okay. So that's almost matching the same time. So hopefully I should start seeing events coming through, but again, it takes its time. Okay, unfortunately, that's taking a bit longer than I expected. But you can see anyway, the other one where we could see the events coming, right? So, okay, that's all I wanted to show you. Let me, yeah, I will keep it running and then maybe I'll have a look later. Cool. Okay, so that was for the demo. I hope that was helpful for you. And yeah, that's all. Now is for questions, and hopefully I can answer them. Otherwise, we can follow up offline. And I also included a few references as well for you to actually learn more about these features. Thank you.
Thank you so much, David. Can you hear me? Yes.
Yeah.
Okay, perfect. Let me see if we have questions here. I think we do. So first, I need to have both SDKs, Java and Python, installed locally before deploy from local computer to Dataflow. Sorry, let me rephrase. Do I need to have both SDKs, Java and Python, installed locally before deploy from local computer to Dataflow?
Good question. I think you need for example, in the example I just presented, you need obviously the Python one, and then yeah, you need the Java a JVM as well, because it will actually check some things and some dependencies from the Java side. So yeah, you need a Java environment and a Python environment. Yeah.
Okay. Another question: how can we write pipeline tests in case of multiple SDKs, Java and Python? In case of Java pipeline, we can use like JUnits or Mockito.
Mhm.
Any info on this will be helpful.
Yeah, very good point. The way you typically will do that, again, you have the different SDKs, right? So within the different SDKs, you will have, for example, a Java transform, and then you will be able to unit test the method, the transforms, whatever you're doing there, right? So we have actually test methods to test in Java and also in Python. So you will run and you will test them independently. So that will be the first step, is to for every single, let's say, stage or step on the DAG, you will test these things as a unit test, as a unit component for the Python and for the Java. So you will have a different projects, right? Because you will have different personas in one and the other. So let's say I'm the Java developer, so I will be in my IDE. I will be implementing the Java part on Kafka.io, so I will just be testing like I always do, right? Then on the Python side, I will test things as a unit test. I don't want really to introduce side effects. So typically what you want as a unit test is to test the logic that you have under control, which is, for example, I don't know, your TFX or whatever you're doing with your Python logic, right? So again, you will apply the same principles there on a different IDE. Now, the next step is obviously integration test, where you need to test the whole thing, right? That's a different story. And for that, yeah, what you will typically do is, for example, running everything as a direct runner, so kind of locally. So that will do a test without having to deploy the entire thing into a cluster. And then obviously you can mock up some of the input data and then validate things, integrating things, and then using a control data set that you have, right? But with the direct runner. Yeah. I hope that answered the question. It's basically two steps, right? Unit test and then integration test with direct runner and with mockup data. Yeah.
Okay, well, this is a question from Sathia. If that didn't answer the question, she will say at Slack. And we have another question from Meng. How to implement JDBC IO in Python SDK for reading data from SQL database?
A SQL data, SQL Server
SQL
database?
database. SQL
Okay.
database, yeah.
So yeah, I mean, I think there is a JDBC IO also available as a wrapper that you can then call from the Python SDK. So you will use the JDBC IO available in Java to make that call. So you can do that as well. Same way I did with Kafka IO, you can do that with the JDBC IO. Yeah.
Okay. And I'm just waiting. Somebody was typing something, but it's not typing anymore. So I was waiting to see if that was a question. The persons who asked are saying thank you, Casio, Sathia, and Venk. And well, we don't have any more questions right now. I was already also checking the YouTube, but we don't have anything there. So I guess thank you, David. I'll invite you to the Slack if you are not there.
Yes,
Sorry.
please. If you have any other
Yes.
questions, I will follow up.
Yeah. If you go to the Beam College website, if you go to the live where we are transmitting the live, there is a link to the Slack at the top. So sorry, but I'll share it right now with you. So you can come to the Slack, and if anybody else has a question, you can go ahead and continue the conversation with David there. Thank you so much, David. And let's continue. Our next session will be in 20 minutes.
Cool. Thank you for having me as well. And have a nice weekend. Cheers. Bye.
All right. Thank you. Bye-bye.
Hello, everybody. Welcome to our next session in Beam College. We are heading into our third session for today, for our third day of sessions. And we are with Bojuan Zhang. Hello, Bojuan. And Bojuan will talk to us about how to build a source with splittable DoFuns. So please carry on, Bojuan. Thank you.
Yeah. So hello everyone, I'm Boyan from Google Cloud Dataflow, and today I'm holding this session to talk about how to build Beam source with splittable DoFun. We are going to cover several content here, so because we are going to dive into the details of building source, and I'm going to compare every aspect with the existing bounded source and unbounded source API with splittable DoFun API. So before we dive into the details, I will first talk about what is a bounded source and what is unbounded source, and then I will introduce a little bit more on what is splittable DoFun and why we want to use splittable DoFun. And then we dive into the details. And if we still have several time left, I will introduce a little bit more on some advanced usages we can do with building source on top of splittable DoFun. So let's go to the first part. What is bounded source and unbounded source? Before we introduce splittable DoFun APIs, we actually have we already have the bounded source and unbounded source API. We offer to the Beam authors to write their own source. And the bounded source is for the authors who write the source to read from a finite set of data, and it's in a batch pipeline. For example, the file IO, radius IOs, they are the bounded source. For building bounded source, the most important things we really care about is the speed of the read. We always want the read happens as fast as we can. So in that case, we usually want to have the more parallelisms when we do the reading. And there are several APIs related to the building bounded source. The bounded source is the first one, and then we also need to create a bounded reader for that. And then we go to the unbounded source. It's usually read from an infinite set of the data and in a streaming pipeline. So for example, the Kafka IO and the PubSub IOs, they are very popular streaming IOs in the streaming world. And the key points for the unbounded source is we always want to make sure that we are tracking the watermark, we are advancing the watermark correctly, and we are able to perform the checkpoints correctly. And we also want to make sure that we are able to do the drain correctly. And the related APIs to the unbounded source is first you need to create an unbounded source, a class, and then you need to create an unbounded reader, and you also need to create a checkpoint mark to perform the checkpoint and to perform the finalize the checkpoint. So given that, let's switch to the what is splittable DoFun. Based on the naming, you can see that a splittable DoFun has two parts. First, it's a DoFun, and then it's splittable. It's a DoFun means it has all the same syntax as a DoFun, so it's pretty simple and straightforward to the current Beam users. So you still can use start bundle, finish bundle, process element for your splittable DoFun. Especially the process element is always the major function body for your splittable DoFun. One point is that you cannot use the user timers and user states in your splittable DoFun. It may not be hard to support it in splittable DoFun, but we decide not to do so. But in the future, if we get many feature requests on that, we definitely will support it. And given that it's a DoFun, it always have an input and the output. So for the splittable DoFun, you will provide an element, and during the execution time, we will spend the element pair with the restriction. So the actual process element function will get a element and restriction pair, and based on that, the process element function will emit the records from that. So usually, when you're building a source, the element is always a metadata or a source descriptor, which can describe what kind of things you want to read. And the restriction usually describe the amount of the data come from that source descriptor. So for example, in Kafka, we use a topic partition as an element to describe which topic and partition we want to read from. And for the restriction, we are using an offset range to describe the offset for each record. So for the initial one, we will use 0 to infinity as the restriction. And then what the splittable means for the splittable DoFun. Imagine that we're reading from the data channel, and it's kind of like easy. We can split at the data channel. So what that means, let's say we have 3 elements to read, and currently we have read the first 2 elements, and we have the last one left. So it's easy to perform a read between the second and to return the last element back to the runners. But the power of the splittable DoFun is we can also split inside one element. So that means giving an element and a restriction pair, we are able to split the restriction. Then we will have the element with the first part of the restriction, and we will have the element with the rest of the restriction. And we can give back the second part of the restriction to the runners, and the runner will reschedule that part on another workers. So it's a very important part for this splittable DoFun, and we will look into this in details in the following slides. So let's look into the code example. It's in Java, and it describes a very simple splittable DoFun. So you can see for here, it's a DoFun DoFun. Yeah, it stands from a DoFun interface, and then it's a major process element function body. For here, you get the element, and here is a restriction tracker. For this tracker, it's a tracker to tracking your restriction, and you can give the definition of the restriction tracker by use new restriction tracker. The reason why we not have here is because for offset range, we actually gave a default implementation to get a new restriction tracker. So this is a major function body. It's basically get the current restriction from the restriction tracker and continuously output records from that restriction. And here is the initial restriction part, which is from the very beginning for a given element, we want to have an initial restriction pair with that element. So if you implement the get initial restriction function, you will have the power to do so. So this is a very simple code snippet to give you a sense of what is splittable DoFun looks like in code way. And let's look into the execution part of the splittable DoFun. So when you write the code like this one, how does the runner execute it? The runner will run an expansion of the splittable DoFun into 3 steps. The first step is pair each element with the initial restriction. The initial restriction is defined here. And then after this one, these steps will output a pair of the element and the restriction, and then go to the second steps. The second step is split each restriction into several parts. So this one is by the split restriction interface. We will talk about it later in the initial split specific. And after these steps, it will output many pieces of the element and restriction pairs and go to the process element function body, which is defined as a process element. This process element function will take element and restriction pair as input and output any records or any data you want from your source. And then when the checkpoint or split happens, this process element function will also give back the residuals, which is also in the element and restriction pair format. So this is how the splittable DoFun get executed in the runner side. Given that we already have the existing source API, like I introduced a little bit before, a bounded source and unbounded source, why we still want to introduce a new source framework in Beam? So the first one is currently, splittable DoFun is able to provide parity to the current source APIs. So that means all you need from your current source APIs, you can rewrite everything in splittable DoFun. And secondly, is splittable DoFun is the only I/O framework for portable execution. Currently, the Beam are under a happy migration path from the old execution world to the portable execution. So that means in the new world, splittable DoFun will be the only source API. And the third part is, as Yumi mentioned, that in the old world, we have bounded source for batch, and we have unbounded source for streaming. So that means if you are writing application, you are writing a source in with unbounded or with bounded API, and one day you figure out that you want your source working in streaming as well, then you need to rewrite your whole source with unbounded source API. But Stable Dufan is a unified model for both batch and streaming. So that means as long as you offer one implementation within Splittable Dufan, you are free to switch with between batch and streaming. So it will be super easy and straightforward for most of devs. And lastly, what is the most powerful point for Stable Dufan is, as I mentioned, that bounded source and unbounded source has to be the root node of the pipeline. But Stable Dufan is a Dufan. It can be any node of the pipeline. So that means you are going to be able to have the source-like operations at any positions of the pipeline. So let's imagine one application. If we store our topic partitions in a BigQuery table, and we want a pipeline kind of like read from the BigQuery table first and get the topic partition we want to read from. Then we want to have the Kafka source to read from that topic partition and the image records. Without Stable Dufan, there's no way to do this kind of things in a one pipeline. But if we can write our read from Kafka on top of Stable Dufan,
Hello, sorry, we had a bit of a technical issue. The cloud does fail a bit every now and then. We had a hiccup, but we're ready to continue. Sorry about that. And Bojan, please carry on.
Yeah. So given that we already know the benefits of using split fund, so let's go into the really exciting part of the building source. So the first one is size estimation. When we're reading from the source, we usually want to provide the size information to the runners. In batch, when the runners get the size information, runner will be able to make a split decision, and that split decision will help us to do the dynamic split in the execution time. So we will have more parallelisms, and our read will happen more fast. And in streaming, the size estimation usually means we can give the backlog information to the runners. When the runners get backlog information, the runner is able to scale up or scale down the worker pools. In that way, the streaming rate will happen more efficiently. So for the given that if you want to do the size estimation, the APIs you can use is in bounded source is bounded reader get estimate size bytes, and the unbounded source is unbounded reader get split backlog bytes. So so that means if you are already familiar with the concept of bounded source and unbounded source, and you know that you want to have these two pieces get implemented, so that means when you switch to the splittable DoFun, you want to implement the get size information, get size interface. So if you provide the get size function, the SDK side will query the size on the element and restriction pair. But it's also okay for you to not provide that function, because SDK will also query the restriction tracker progress to get the size information. So let's look into the Kafka example, which is a simple code snippet of how we do the size estimation. In the left side is a splittable DoFun code snippet, and on the right side is the unbounded implementation. So you can see we first implement the get size annotation, and then the given element is a Kafka source descriptor, which I mentioned is always the topic and partition, and then we also have the current restriction. When the function gets this two, it will look into the current offset range and get the how many records we have output and how many records left behind. And then we will give the average size. Then we actually keep the average record size in memory, and when we get all of the informations, we will return the average size multiplied by the element remaining. So that's the size information we give back. And in the unbounded reader implementation, it actually does the similar things. It queries a backlog and gives that backlog back to the runners. So if we, given that we already implement the code, how does the runner can know the size and how this function get invoked? So let's look into the expansion again. So as I mentioned before, the splittable DoFun will be expanded into several steps by the runners, and the size estimation will be evoked in the split and the size restriction. So that means after you split your restriction into several pieces, and before you output, the SDK harness will call the get size function on the split on the element and restriction pair, and then pair the size again with the element and restriction, and output to the next steps. And every time you do the checkpoint or the split from the process size element and restriction, we will also call the get size on the element and restriction, and all of the information will be available for the runners. So given that after we have the information back to the runners, how can the runner know the size? So what we do is by encoding and decoding. For each element restriction and size pair, we are using a Kiwi coder and a double coder to encode the values. And we know that Kiwi coder and double coders are well-known coders to both SDK and runners. So that means when the runners get the element restriction size pair, the runners is able to use first the Kiwi coder to decode the values into a something key and the double value, and then again use the double coders to decode that value again to get the size. So that's how the runners get size informations. And then we go to the initial split. Initial split usually is the first parallelisms we can give to read from the source. It happens before the read actually happens. It's especially important in streaming because we don't have the dynamic split for streaming. So the initial split will give all of the parallelisms from the very beginning for the streaming pipeline. If you want to provide such abilities to your source in unbounded source and bounded source, it's a split. You can implement the split APIs to give that parallelisms, and in Sublible DoFun, it's called split restriction. So let's look into the code snippet. So as you can see that we also have the left side is the Sublible DoFun implementation, and the right side is the unbounded source implementation. So let's look into the unbounded source one first. The Kafka I/O will take a list of the topic partition as input and split that list into sublists, and then distributed this list of the topic partitions on different workers. So basically, one shard of the Kafka I/O will include a sublist of topic partitions. And then let's switch to the Sublible DoFun implementation. As you can see here, actually, we are not going to split the restriction. The reason is that the initial split happens on the different level for Sublible DoFun and unbounded source. For unbounded source, the initial split happens at the source spec. But for Sublible DoFun, the initial split happens at the restriction level. So that means Sublible DoFun will give a more fine-grained splittability level things. In Kafka I/O, we already have each individual element, to be a single topic partition. So in this case, actually, we are having the same initial parallelisms as a unbounded source. So we are not. So in this design, we are not going to split the restriction into further shards. After we implement this code, how does the split restriction get invoked by the SDK harness? So it's still through the graph expansion. And after we do the initial restriction, and it will go to the split and the size restriction. This step will invoke the split restriction function and output all of the shards of it. And given that we already split the restriction, how does the runner to redistribute these shards on the different workers? The answer is the runner will insert a reshuffle between the size and split restriction and the next process steps. So the reshuffle will help us to redistribute these shards ideally on these workers. And then we will go to the execution step, which is really read from the source descriptor and output record. So during the actual reading steps, we always want to provide the progress information back to the runners. The progress usually includes two parts: how much work has been done and how much work is remaining. And this information is important for the runners. There are several aspects. So first one, the runners can show progress information on the UI. Then the end users can know which read step is slow and which step is fast. It will be helpful for the users to tune their pipelines to gain a better performance. And they even can change their source configurations to have a better read experience. And more importantly, the progress is a very important signal for the runners to make a split decision. So if you want to get benefit from the dynamic split, you want to provide a good progress. And how can we do that? In the bounded source, the API is bounded reader get fraction consumed. So the fraction consumed will describe how much work has been done. So we can use 1 minus such fraction to get how much work is remaining. And in unbounded source, actually, we only care about the backlog because it's a streaming pipeline, and we only focus on how much work are left behind. So the API is get split backlog bytes. And in Sublible DoFun, you can always implement a head progress phase for your restriction tracker, and that will give the progress information for the runners. So let's look into the code snippet. In the left side, I'm demonstrating a restriction tracker, a part of the restriction tracker that we used for the Kafka I/O, which is called Global Offset Range Tracker. In this function, the function will give the progress information, which contains two parts. As I mentioned, the work has been done and the work is remaining. And on the right side is the existing unbounded source implementation. And you can see it's query the backlog and give back the backlog information. So after we do the implementation of the code like this, how can the runner and SDK communicate with each other on this progress? So let's look into this execution graph. The SDK and the runners communicate with each other via Fun API channel, which is a portable execution I mentioned before. And the right side, the blue box, represents a portable runners, and the left side represents the SDK harness. During the execution time, the portable runners will issue process bundle progress request periodically to the SDK harness. And there are many threads, and the two notable threads in the SDK harness one is the processing thread, which is calling your do from process element functions, and another thread will listen to this request and do the corresponding actions. So when this thread get the request, it will call the current tracker get progress, and it will have the progress information from your tracker, and then use process bundle progress response, send that information back to the runners. And the runners will look into the response and get the progress information it needs. So as you can see here, we are having two threads in parallel, and they both access to the same object, the tracker, right? So you may worry about the multi-thread safety concurrency issue. In current Java SDK implementation, we handle that for you. So in your implementation, there's no additional work need for you to provide such safety. So that's one thing we want to keep in mind. So as you can see, the whole point for this splittable DoFun is have the interface and has the implementation as simple as possible and have the runners to do the heavy work. After we offer the progress, as I mentioned, the runner is able to issue a split. So let's go to the dynamic split in batch. Dynamic split is a powerful tool in batch to have the readers happen fast. So it usually splits the current read into the primary, which the things we want to keep on the current workers, and the residuals, which is the things we want to return back to the runners, and have the runners which schedule on other workers. So let's look into the execution, the green execution graph. So here we can treat the green bar as a continuously read, and we are reading this kind of shards in parallel. And as you mentioned, you can notice that there are two very long green bar, and during these two very long green bar, other workers are idle, and we have to wait for these two green bars to be finished, and it's not ideal, right? But with dynamic split, what we can do is the runner is able to notice that there are two very long outstanding work, and the runner is able to split these two work into other shards and keep something in current worker and redistribute other works on the other workers. Then we will have this nice evenly redistributed works graph like this one. So we will have all the workers have the available work to do, and we will have a faster read. So it's an ideal world. In order to do so, we offer the APIs in bounded source is split at fraction. The fraction is a double value that the runners computed based on the progress we provide to the runners. And in the splittable DoFun, it's restriction tracker tries split at a certain fraction of remainder. And this is the same. The fraction is also computed by the runner. So let's look into the execution graph. The reasons why I not put the code snippet here is Kafka IO is a streaming source, so we don't have the dynamic split there. But I will present the same ideal code when we talk about the streaming checkpoints. So the SDK harness and the runner harness again communicate with such a split via portable execution, which is Fun API channel. And during the execution time, the portable runners will compute a split decision and send this decision with process bundle split request to the SDK. And when the SDK gets such split decision, it will say, I want the current tracker split at the fractions that the runner provides. and send back the residuals with process bundle submit response to the to the runners. And the runner will look into the response and reschedule the residuals. And let's look into the streaming checkpoint. I have mentioned that for batch we have dynamic split, but in streaming we are not going to do the dynamic split because the read in streaming is infinited, and we are not able to know the end of the read, so it's not able to perform some split in the between. But we are able to do the checkpoint, which means we want the current read finished as soon as possible, and we will redistribute the residuals on the other workers. So you can assume that when we do the checkpoint, the fraction remainder is always 0. And the APIs related to this functionality in unbounded source is unbounded source get a checkpoint mark. If you want to do this, you have to first to implement this function, and second, you need to create an object which inherited from the checkpoint mark. But in Sublable Tufan, all you need to do is you implement the restriction tracker trasplit, and in your function body, you can say you can assume that the fraction of remainder is always 0. So let's look into the Kafka example. On the left side is a partial code of the global offset run tracker we used for the Kafka, and it implemented the trasplit function. And for a given fraction of remainder, we query the current possible end as the things we estimate, and then we stop the current read immediately and return that part of the residuals into the split results. And similarly, in the unbounded source implementation, you can see it actually put the next offset as the checkpoint mark and return it back to the runners. And this checkpoint will go through the same split channels as I mentioned here. It will go through the same things as the dynamic split. So it will also go with the process bundle submit request and the process bundle submit response. And if you are familiar with unbounded source, you may want to say, after we do the checkpoint, how do we do the similar things as we do in unbounded source for finalized checkpoints? So in unbounded source, you usually do the finalized checkpoint by providing a function called finalized checkpoint mark. And in with Sublable Tufan, there are actually two major ways to do so. The first one is you can use bundle finalization, and the second one is if bundle finalization doesn't work for you, you can build your own transforms to perform such purpose. And the reason why we want to finalize checkpoint is sometimes we may have the case kind of like after we commit all of after we output all of the things to the runners, and the runner is able to say, I'm done with the current bundle and I will never replay this bundle again. In this case, we may want to tell the external source that I have done this portion and I want to commit such offset, and you can clean up all of the things before this. So if you want to do this kind of things for your source, you may want to consider to do the finalized checkpoint. So let's look into the examples. For Kafka IO, we actually built a transforms to do so. So in this case, in this case, you can see we expand current transform. We create a commit transform, and the expansions look like we will window the output into a 5 minutes fixed window. Then we will do the compute the largest offset per key, and then we will commit the offset back to the consumer. And in the unbounded source implementation, it almost does a similar things. It always finalizes the current checkpoint, which means it always commit the current offset to the consumer. And let's look into the bundle finalization way. So this is a part of the version of PubSub Lite IO, which use bundle finalization to commit offset. So this is the Sublable Tufan process element body, and you define a bundle finalizer here. This is a built-in mechanisms for the SDK, and then you register your callbacks here. Then you have done. So that means you can you provide a notion says I want to use bundle finalization, and you register callbacks. This is the things I want to do when I'm trying to do the finalization. So that's all the things. After you define this code, how can the SDK set communicate with the runner set to say, I will perform such finalization? So again, it's over the Fun API channel. So here is the execution graphs. When the runner starts to send a process bundle request, and the SDK accept this request and spin the graph and do the execution, the SDK will look into your function, and it will notice that you define a bundle finalizer, and you register the callback. In this case, when this bundle finishes, the SDK set will send back a process bundle response with the request finalization equals 2 to the runners. When the runner gets this response back from the SDK, the runners will do a calculation, do some storage, and after the runners can consume that it will never replay this bundle again, it will send a finalized bundle request to the SDK. And when the SDK gets this request, it will look into the callbacks you register here, and then call the callbacks to perform the finalization you defined, and send back a finalized bundle response to the runner. So that's how the finalization works. One point here is bundle finalization is always the best effort for the runners. So that means the runners can choose not to perform the bundle finalization. So that's why we built a commit transform for Kafka, because we know that's his best effort. We may have a chance that the finalization will be never called. So, but in our case, we won't have the consumer to commit offset all the time. So that's why we built a transform. So when you're building your source, you may want to make a judgment here. So if you think it's okay for you that several finalization will not be called, you can use the built-in finalization mechanism. But if you think it will bring you a huge issue if you never call back, then you may want to build your own transforms. And then after we talk about all of the things here, I want to introduce a special things which is very unique to Stability DuFang. So that means this self-checkpoint functionality is only provided by the Stability DuFang. The existing bounded source API and non-bounded source API doesn't have the ability to do so. So what means self-checkpoint? It means the Stability DuFang is able to resume processing current element restriction and send back the residuals to the runners. And after a certain time, the runners will reschedule the residuals, and the SDK harness is able to resume from that checkpoint. So let's look into this small graph here. So let's say our DuFang are reading two element restriction pair. So let's use Kafka as example, which is one topic partition offset range and another topic partition and another offset range. So in this case, when we look into the first topic partition, there may be no available record at this time. So without self-checkpoint, we have to wait at that moment until something comes into this topic partition. But we know that the second element actually has several records. In this case, because we have to wait at the first element, we will never have the chance to read at the second element. So it's bad. But with self-checkpoints, what we can do is we look into the first topic partition and we notice that there's no available record at this time. So we want to resume processing the current topic partition and we want to switch the next topic partition. So that's what the self-checkpoint does. From the API's perspective, if you want to perform such functionalities, all you need to do is in your process element function body, you return the process continuation resume at the place when you want to do the self-checkpoint. So let's look into what we do for Kafka I/O. So this is a major function bodies for the Kafka I/O. It reads from a topic partition and output all of the available records. And as you can see here, we're trying to do one pull from the consumer and we check whether the current records are empty. If the current records are empty, that means there's no available records from the current topic partition. Then we return resume, which means we want to resume processing current element restriction pair, and we want to move to the next one. So it's very simple, right? So you just need to make a decision and return the resume here. Then after we do the self-checkpoint, we return the residuals. How does the runner reschedule it? So let's look into this one. We will have the residuals as part of the process bundle response. And so this is all done by the SDK harness. When you write your process one like this one, and you produce certain resume mark from your function body, the SDK harness will get the notification, and the SDK harness will collect all of the residuals you produced from your submissible DoFun and send it back all together with process bundle response. When the runner gets the process bundle response, it will look into whether there are residuals in this response and reschedule them. And how does the runner get this residuals? Like, let's look into the Protos definition for the process bundle response. The SDK harness will feed your produced residuals in the delayed bundle application format, which called the residual roots. So the runners will look into this field and get the residuals and send the residuals to other workers. So that's how the runners reschedule their things. And then let's talk about something specially to streaming. The first one is watermark, and I will also talk about the dream. In streaming, the source is the producer for the watermark. So we always want to make sure that source are tracking the watermark, advancing the watermark correctly. In Sublimable DoFun, we offer a class called watermark estimator for the Sublimable DoFun authors to tracking the watermark. We also provide 3 common tabs for the watermark estimator. The first one called wall time watermark estimator. So based on the name, you can know that the wall time will always use the current processing timestamp as the watermark. And the second one is monotonically increasing. And this one will use the record timestamp as a watermark, and it will always use the maximum value of the timestamp as the watermark. In this case, the monotonically increasing watermark estimator expects that every timestamp it gets is increasing monotonically. If it is not, it will throw exceptions from the watermark estimator, and your DoFun will be killed. And the third one is the manual watermark estimator. So based on the name, you can see that you can use this manual watermark estimator in your process element function body, and you can set the watermark by yourself, no matter what the value is, as long as it makes sense to you. And there are 2 parts in the submissible DoFun when you're trying to track the watermark. So the first one is you need to create a watermark estimator, as I mentioned here, and you need to tell the submissible DoFun what kind of watermark estimator you want to use. So that is new watermark estimator interface does. You implement this interface and give the type of the watermark you want to use. And the second part of the tracking watermark is to set the watermark in your process element function body. So let's look into the create. So let's look into the create watermark estimator first. But before that, let's look into the how we track the watermark in the unbounded reader API first. So basically, that is in the unbounded source, we have a APIs called get watermark from the reader. And what the reader usually does is look into the every element, every record is going to produce, and get the record timestamp as the watermark. And let's look into the submissible DoFun implementation. So this is part of the implementation which gives back the watermark estimator. So as you can see, it implemented the new worker estimator interface and give the things it wants. For Kafka IO, we actually are using 2 kinds of watermark estimator. We use manual watermark estimator, and we also use the monotonically one. And then let's look into how we set the watermark for the watermark estimator. In this process element function body, we output the records. And when we know that currently we are using the manual watermark estimator, we will set the watermark for that. But if we know that currently we are using the monotonic one, all we need to do is we say we want to output with timestamp, and we give the record, and we give a timestamp. The SDK harness will have your watermark estimator track that output timestamp as a watermark. So in short, that means, let's go back to here. So for these 3 common tabs, for wartime and the monotonically increasing one, all you need to do is you implement the new watermark estimator interface, and to say, I want to use this 2 candle watermark estimator, and you make sure that every time you output a record, you also output it with a timestamp. That's all you need to have to do. But if you are using a manual one, you have to first give back the watermark estimator tab, and the second, you want to set the watermark manually in your process element function body. So that's how we track the watermark in the splittable do file. So and after we report the watermark, with the watermark estimator, how can the runner get the information? So we usually report the watermark back with 2 things. The first is when the self-checkpoint happens, we will report the watermark together with the process bundle response. Or if the runner issue the checkpoint, which is streaming checkpoint happens, we will return the watermark information together with process bundle split response. And they are all in the same place, which is delayed bundle application field. And this delayed bundle application will contains a map of the watermark. Usually what the runner does is it will look into this field and get the minimum timestamp of all of the current watermarks as the watermark. So that's how it does and how it gets back to the runners. And then let's look into the Gin. Gin is kind of like special operations for data flow, and it is a way that data flow offers to the users to cancel their pipelines or to stop their pipelines. So usually if you want to stop your pipelines, there are 2 ways. You can cancel your pipelines directly, which means the pipelines will discard everything it's in flight and just finish it as soon as possible. And the second one is Gin. So that means the pipeline, the source, will not produce any new records, but all the in-flight data will be finished inside the pipelines and then stop it. Within the bounded source, within the unbounded source API, there's no way for the customers, for the SDK users, to customize the weights of Gin. The unbounded source will just stop the read immediately. That's the default behavior. But for the splittable do file, we offer APIs for the source authors to customize the behavior. So that's called truncate restriction. From the name, you can see the function is supposed to truncate an infinite restriction into a finite restriction, and the finite restriction should be able to finish. So this is how they when you write your source on top of splittable do file, how can you configure the Gin behavior? But it's also okay for you to not implement the truncate restriction, because we also provide the default implementation, which is stop read as soon as possible, just like what we do for unbounded source. So after you define this function, how does this function get invoked by the runners? So this is another round of the graph expansion. So runner will do this kind of things to do another round of it. So the left side is the normal process element steps, and it will keep processing until you click the button on the data flow UI says, I want the pipelines to Gin. After the runners get the signals of the Gin, it will change this portion of the graphs into this portion of the graphs, which it will insert a truncate restriction steps right before the process says element and restriction. The truncate restriction will invoke your defined truncate restriction function, which cut the given restriction into a finite one, and then populate into the process element again to have it finish processing. So that's how the Gin is performed on the splittable do file. Okay, yeah, so that's all of the things I want to talk about how to build source on top of splittable do file. We are talking about 8 points of it. There are some specific to batch, for example, dynamic split, and there are something specific to streaming, for example, Gin So I also want to talk a little bit more on the advanced usages if you build your source on top of Stable Diffusion. The first one is deduplication in streaming. So that means if you are writing a streaming source and you want to do the deduplication after you output the records, there's no additional work for you because we already built a deduplication transform in the SDK side. All you need to do is you can assemble that transform into your pipeline. And the second part is the things that I really want to highlight is Splittable Diffusion is a Diffusion. It can be any node of the pipeline. That means your source can be any node of the pipeline. It is no longer to be tied into the root node of the pipeline. So please keep that in your mind. And why that's very important is because it will give the more possibilities of the application scenarios. So for example, for Kafka, we build a dynamic read functionalities. So what that means, when we with the unbounded source API, the Kafka IO has to be know the partitions it's going to read from during the pipeline construction time. When it starts reading, if the Kafka topic want to do the repartition, it will lost the new partitions added into that topic. But now we have the dynamic read. What we can do is we always pulling the available partitions from the topic, and we emit the new added partitions down to the Stable Diffusion implementation of Kafka IO. And that Stable Diffusion can continuously read from the new added partitions and output the records. In this case, there's no need for the pipeline authors or the pipeline managers to restart the pipeline over and over again after repartitions. So it's super powerful. So please keep that in mind that your source can be any node of pipelines. And the third one is with the Stable Diffusion implementation, you can create cross-language transforms as long as you implement certain given interface. So that means if you write your source, for example, in Java SDK, then you are able to use your source from the Python pipeline. It's also very powerful. So basically, that's all the things I want to talk about. And finally, I want to share this with you. So I list all of the interesting reading materials and all of the tutorials I have for the building source with Stable Diffusion on these pages. So if you are interested in learning more details or reading more things, this is definitely the things to go. So yeah, that's from my side. Let's go into the Q&A session.
Thank you so much, Boyuan. And sorry to everybody for the technical issues we had. We had some hiccups, but I mean, Bojuan was very kind to restart the slides where we had issues. So thank you so much, Bojuan. And we're on time. The next session starts in 3 minutes. So if you have any questions about this, we know that this is an advanced topic, and some of you may just be getting started doing this. But Bojuan can if you have any questions or would like to know more, please feel free to contact her. Bojuan put her email at the beginning at the first slide, but also I don't think you're in the Slack for Beam College yet, Bojuan. Are you?
I will join it later. And
okay.
I also want to say that if you have any questions related to Beam any topic, please contact us via the dev mailing list. We have many experienced folks there to help you.
Yes, definitely. And just so everybody to remember, that's dev@apachebeam, apache.beam.org. Okay?
Correct.
Well,
yeah, that's one.
Thank you so much, Bojuan. And to everybody else, in a couple of minutes, we'll continue with the last session for the day. Thank you and have a great weekend, Bojuan. Bye.
Hello again. We are with our next session. We have a team. We have 3 speakers right now. Everyone is from Akvelon. So first we have Alex. He's a program manager at Akvelon and leader of professional services delivery. He focuses on helping customers design and build technology solutions. Welcome, Alex. And we also have Arthur. He's a technical lead at Akvelon. He has a wide range of strong practical experience in big data, machine learning, and web development. And he is BIM and Dataflow templates contributor. Oh, wow. And we welcome Arthur. And we also have Ilya. He's a technical lead at Akvelon, where he's focused on data engineering. Ilya has a strong experience developing big data technologies and machine learning systems. He is an Apache Beam and Google Dataflow templates contributor. And guess what? They are going to be explaining Dataflow templates, how do they work, and how to create them. So welcome all the speakers, and go ahead.
Thank you, Mara. Thank you for the introductions. Hello, BIM community. It's our pleasure to be here, and welcome to Dataflow templates session. Today, we're going to present what Dataflow templates are, an example use case that demonstrates a Dataflow templates benefits, and we'll go into some highlights of the solution and demo an example solution that we built. We also will talk about how to get started contributing an open source Dataflow template to the community, and we'll have a Q&A session at the end. Akvelon is a custom software engineering company, Google Cloud partner, headquartered in Seattle, Washington, with engineering offices in Europe and North America. I'm a program manager with Akvelon, and together with Arthur Hanin and Ilya Kozyrev, we focus on data, analytics, and machine learning solutions. Our team contributed several Apache Beam complete examples and Dataflow templates based on Google Cloud customers' use cases and other enhancements as well. What is a Beam pipeline? Pipeline is a flow of operations in Beam. In the simplest way, it starts with an I/O read, then a series of data transforms are applied, and I/O write transform writes data to an output sinks. Users run pipeline from their development environment. The Apache Beam SDK stages files on Google Cloud Storage, creates a job request file, and submits the file to Dataflow service. Dataflow templates is a way to package and stage pipelines that is easy to share on your project in your organization and does not require setting up an Apache Beam development environment in order to just create Dataflow job. Template has 2 phases. Construction phase is implementing pipeline, compiling it into execution graph, and staging on Google Cloud. And execution phase allows to run templates using Google Cloud Console, like you see on the screenshot, a command line gcloud tool, or REST API calls, without the need of the Apache Beam development environment and associated dependencies on your local machine. Runtime parameters allow to customize execution of pipeline and templates. Running pipeline does not require recompiling the code every time. There are 2 template types. Classic templates are permanently fixed execution graphs that are stored on Google Cloud Storage. Classic templates require pipeline code modification to implement value provider interface if you want to support parameters and run variable when the template is run. For example, if you want to pass a name of the PubSub subscription to your template. And a change in the template, like adding a new input source, Google Cloud Storage, for example, will require to recompile the template. There is a newer template types, flex templates. Flex templates package the existing pipeline as a Docker image and stage Docker image on your project's container registry. They also create template specification file and store it on Google Cloud Storage. Then to execute Flex template, just refer to the template spec file. Based on our experience, Flex templates provide more benefits and easier to use than Classic. Benefits of Flex templates are dynamic execution graph that is constructed and also validated at job launch time based on final parameters that user supplies to the template. For example, a template can support PubSub and GCS input sources and will construct pipeline execution graph based on the supplied parameters to specify the input source. Flex templates eliminated need for value provider interface, improving developer experience and expanding I/O options available. Creating Dataflow Flex templates has 3 steps: implement pipeline, create metadata, and build the template. We will dive into steps to create pipeline and template in our presentation and cover in the demo. We will start introducing a use case where template was helpful to support a variety of runtime options for the pipeline. Customer use case was to ingest large volumes of data that included sensitive data like credit card numbers or PII, and a third-party data protection service was used for tokenization, converting sensitive data elements like credit card numbers into non-sensitive characters, a token representation that can be safely stored. Based on access role, a user may see a token representation data, a partially masked data like last 4 digits of a credit card number, or an original credit card number. Dataflow provides an auto-scaling, fully managed cloud service to run Apache Beam pipelines with consumption-based pricing and was great for this data processing. Challenge was that out of the box, there was no support for calls to third-party service to tokenize the data. We built custom data pipeline to implement this, and the pipeline also needed to support different data formats, different input sources and output sinks. But the actual processing of the data remained same. Templatizing this pipeline helped to support all different I/O and execution options using template parameters and making a template great, easy to use building block here. Next, Artur will guide us through the architecture and technical highlights of this solution.
Thank you, Alex. Thank you. So, as you already know, my name is Artur, and I am the one who will guide you through the overview of the whole architecture, and then I will highlight the most interesting parts of our solution. And we'll start with the overview of the architecture. As you can see at the slide, the pipeline supports different sources and sinks. It can take JSONs, CSVs, or Avros from GCS, and stream data from PubSub. Then, it tokenizes data via remote REST calls to the third-party data security service. You can see that this service interacts itself with the policy storage. And finally, the pipeline outputs tokenized data into one of the supported sinks. These sinks are Cloud Bigtable, BigQuery, and GCS. During the development, we faced 2 main challenges, which you can see marked with 3 orange arrows on the slide. The first challenge was about supporting several input sources and output sinks. On the diagram, you can see it on the left and the right side from the Dataflow template block. The second challenge was supporting and optimizing performance for calls to third-party REST service. This one can be seen a bit higher than the Dataflow template block. We're going to take a look at the challenge I have just mentioned and see what the stateful to fun words in our diagram mean. And we will start from the concept of this mysterious stateful defun. Even though there is no much mystery, its name is nicely self-explanatory. Moreover, yesterday Ken shared great deep insights of stateful and timely processing. We today will take a look at it from another angle, as Beam users. All right, let's begin diving into this. A brief explanation for the defun may sound like this. defun performs the particular transformations over each element. What kind of transformations? The ones that you told it to apply. A stateful defun expectedly means that our defun has a state. Thus, it has the ability to access persistent mutable state while processing each input element. Very important to mention that a state cell in Beam is scoped to a key plus window pair. Let's take a look at the diagram a bit closely. At the first glance, it may seem that every input element which is presented via red squares goes into the state on the right, which is illustrated via red triangles. But it's not the only case. You may have such, and we even will take a look at one shortly, but it's not necessary. These red triangles can be anything that you want to save at the particular processing step. So, as you might guess, we should somehow use these triangles to produce red circles to call our defun truly stateful. Here are some examples where this concept becomes handy. The first one that comes to my mind is deduplication. We want to keep a Boolean value to distinguish if we saw the particular key before or not. Another example is arbitrary but consistent index assignment. Here we want to keep an index in memory and increment it for each data element. The last example I'd like to come up with is anomaly detection using some machine learning models. For example, we can keep machine learning model and its last prediction for the particular user and then use it to make further predictions. Now, let's move to our case where each element goes into the persistent state and after some period of time comes out. Well, this picture removes all suspense. Yes, we use the persistent state as a buffer for our elements. The challenge was to optimize the communication with the REST service. On this diagram, the REST service is illustrated via elegant gray cloud on the right. Stateful defun helped us to buffer and batch data into bundles that worker can send in one request. We even managed to maintain ordering of data between these batches. Well, the time has come to see the implementation of stateful defun. This code snippet is based on the Beam documentation for stateful processing. I can't help but say that the Beam documentation is very helpful for both starting with Beam and going deep down into use cases, technical blocks, or designs. And I'm thankful to Beam community for providing these resources. I'd like to highlight the important parts of this defun, starting with states that are specified here. You can see two of them at the very top of the snippet, buffer and count. Both of them have a type of state spec. Buffer, as you may see, is a bag state, so we have some bag with events. We actually add events into this bug. Count is a value of integer that we increment in order to optimally keep track of the amount of the elements inside of the bag. In this code snippet, we can also see how we update our states. At the beginning, we increment count and add current element to buffer. Then, when count becomes greater than some defined threshold, we process all elements from the buffer and finally clear both states. We didn't stop on pure stateful defun. We also added a timer to it. We came up to the situation with the streaming data when the actual data may appear after some significant period of time. We didn't want the external service to idle, and that's how we added the flexibility. Now there is no matter the pipeline is streaming one or batch. Such construction handles both situations. An initial stateful defun can be quite simply extended with a timer. The declaration is almost the same. As you can see, it uses predefined timer specifications. Then we set the timer somewhere at the process function, in our case, at the very beginning. And the final step is to add actions that will be performed after the timer expiration. It can be done via a function with a non-timer annotation as the last one on this slide. This code snippet plus the previous one are actually everything what is needed to implement data batching. In fact, if you need to implement any custom stateful processing, stateful defun is definitely purposed for this. However, if your case is similar with ours and you're just looking for the data batching, there is another alternative. And it is called group into batches. I'd like to share with you insights we gained during our own researches. When our team was at the very beginning of the development process, we found stateful define concept, and after some diving into it, we were amazed of how easily we can solve our challenge with batching. We implemented our solution, created a PR, and then our reviewer gave us a hint and suggested to consider group into batches. We took a look at it and found out what it is. First, group into batches, well, surprisingly groups your data into batches, the same way as stateful define has a state. Behind this transform lays stateful define, and the actual implementation has a lot in common with code snippets we saw a few slides ago. It is optimized in different ways. There is a data prefetching that speeds up data loading, and Dataflow Runner knows how to treat this particular transform to parallelize processing via auto-sharding. Finally, group into batches is supported in both Java and Python Apache Beam SDKs. You can see this nice Python example with fruits and vegetables on the right side of the slide. No more circles and triangles. Notice that even if some key doesn't have enough data to form a full pack of fruits, group into batches doesn't forget about them, outputting as much as it can. Next, we will see how we enhanced our template with this. This code snippet presents a p-transform that takes a p-collection of key integer and value row pairs as input and outputs p-collection tuple. Please notice that we use some row class to represent our data. Now, let's take a bit closer look at applying our group into batches transform. Firstly, we specify the size of the batch to pass it to a backstate hidden behind. Secondly, we provide a maximum duration for buffering, which is actually passed to the timer we talked about pretty recently. And finally, we apply our tokenization function that takes every batch, sends it to the remote service, and then parses a response to a collection of successfully processed elements and a collection of the ones that failed for some reason. Well, that's it. Now we can batch and beam everything we want. Can we replace every stateful define with group into batches? Well, at least not yet. There are still many situations when stateful define comes more handy than group into batches. To sum up, stateful define is a great and flexible way to customize any stateful and timely processing. Group into batches is a nicely optimized out-of-the-box transform that saves your development time and covers every batching buffering case. That is why deduplication and arbitrary but consistent indexing should be implemented with pure stateful processing, because they don't require any batches. On the other hand, external API calls and data preparation for machine learning models are natural candidates to use batching and optimize it via out-of-the-box solution. Remember another challenge I talked about? Yes, the one that refers to many input sources and output sinks. There was a reason why we noted row class on the previous code snippet. I want to pass the word to my colleague and a good friend of mine, Ilya, who will walk you through our architecture design to address this challenge. Thank you.
Thank you, Artur. Thank you. Let's discuss data representation. As we mentioned before, one of the biggest challenges what we had during the template implementation was data representation. At start of development, we planned to support multiple data sources and data sinks for pipeline. And what is more important for us, we wanted to be able to scale to new sources and sinks with the minimum implementation time. To achieve this goal, we needed a common abstraction for data representation. As we know, in Beam, we have an SMP collection, but the type of element in this collection must meet our requirements. Let's think about requirements for data representation. First, what came in my mind, it should be a common abstraction which we would use with different input formats. It will help us to make our business logic in the pipeline independent of input format. Second, we want to make the transformation to this common abstraction easier to development. We want to have a common pattern or interface to implement new transforms, and will be great to have already implemented transforms to this format included in Beam SDK. And last important thing, what we need to keep in mind, is serialization. We want to have a balanced abstraction, what will be comfortable to use ancient code and effective for serialization. Because as we know, in data processing and big data world, each extra kilobytes for element might be potentially turned to hundreds and hundreds extra gigabytes for all data set. Let's take a look at the common approaches for data representation. In general, all existing common solutions we can split into two categories. First, text-based formats such as XML, JSON, CSV, or YAML. That's easy to understand, and we can usually use it in our code using different libraries like JSON to work with JSON. But there is a common issue for those formats, serialization, because in general, it's string representation format with not very effective serialization process. The second group, binary-based formats, like Avro, Protobuf, Parquet, and MessagePack. In this group, we can highlight Avro and Parquet as the more popular for data processing. Avro is row-oriented format, and Parquet is column-oriented format, was optimized for Java serialization both. Is it a good common choice when we talk about big data process? But from the Beam usage perspective, in case of when we don't want to use generic records, we need to implement additional classes to represent our data as a Java object. That's absolutely fine for some cases where we have a strong data structure and when we don't plan to process any different structures and formats in the same pipeline. But in our case, we try to create a really flexible solution that could process different data formats and structures. In this case, we need to use something more generic and flexible instead of Avro or Parquet. And that is BeamRow. BeamRow fully covered our requirements. BeamRow is a part of Beam Schema API, and consequently, it supports primitives in BeamRow schema. This often match primitives in most programming language, like integer, long, strings, and so on. Also, what's important for us, ordering in the schema will be the same as the ordering in data. What about serialization? In Beam SDK, we have row coder, and row coder is quite effective for serialization. And yes, someone from you might say Avro is more effective for serialization. Yes, that's true. But benefits of row make it more preferable for us in Beam. Using utilities included in Beam SDK, we can parse Beam schema from JSON, and it makes row a fairly generic solution for us. Also, BeamRow supports Beam SQL. It's a very perspective feature that provides us with Zeta SQL syntax to make SQL queries to row-based pre-collection. It might improve analytics in Beam and reduce Java or Python knowledge to implement Beam pipelines. How BeamRow solves our challenge with multiple sources and sinks? We made architecture in BeamRow in center and implement whole business logic in our pipeline around the BeamRow. To support multiple sources and sinks, we use simple function to transform to BeamRow source format to BeamRow and BeamRow to the destination format. And to be able to scale to new sources and sinks, we have a pattern to implement new transformation from and to BeamRow. For the first look, implementation of transforms into BeamRow and from BeamRow might seem too hard. However, that's not. What else is great about BeamRow? There are a lot of implemented transforms that already included in Beam SDK. So let's take a look how you can use BeamRow in the pipeline. And yes, it's time for a live demo. There is demo plan. I want to make template implementation overview. I'll demonstrate how you can organize your pipeline code structure. Together, we will implement new source in the pipeline. It will be Parquet format, and we will use Parquet IO. We will implement transformation from Parquet format to BeamRow. And at the end, I'll show you how easy you can build data flow template from the pipeline and use it in Google Cloud Platform environment. So what we need to do in this demonstration, we need to read Parquet file from Google Cloud Storage using the schema in JSON format to produce Beam row, tokenize it using our example of data tokenization, and write back to the Google Cloud Storage using CSV. All features except Parquet already implemented in this example pipeline. And our challenge for this demonstration, implement the new source, it will be Parquet. So let's go to the main class of the template. This class is very similar as any other Beam pipelines. We create pipeline object, apply necessary transformation for P collections, and call pipeline run. But one thing, what I want to highlight, it's schema. As I mentioned before, we use JSON schema, parse it, and use to produce Beam rows and use in row coders. Let's take a look again on the example of schema. There is very simple JSON with a collection of fields, and for each field, user need to specify a description of each field. There is name, type, its primitives, mode, it might be required, or nullable for nullable fields. Let's go back to main class. This pipeline can work with Google Cloud Storage and PubSub. But in this demonstration, let's focus on Google Cloud Storage. GCS.io, our own implemented class, what contains two important methods, read and write, to read data and write data. And also contains methods to convert input format into the Beam row. So let's think how we can add new source. In read method, you may see switch case statement what go through each supported format for Google Cloud Storage. And we need to add new value here. So let's add it in format enum. We will take it from option for the pipeline. Now we can add new case statement. It will go for the Parquet value, and we need to implement new method. It will be read Parquet. Reads Parquet from Google Cloud Storage, convert into Beam row because read method requires to return P collection of row, and we can call new method here. So let's think about parameters for new method. Because it's entry point for pipeline, we need to apply IO transforms to the pipeline object. And first element will be pipeline. Looking ahead, I tell you about Parquet.io. We will use Parquet.io to read Parquet files from file system from Google Cloud Storage, and Parquet.io requires schema. Let's pass Beam schema, what produced using JSON file. And let's implement new method in the GCS.io. So, how we can read any files from file system? There are two ways: using file.io with generic types, or using some specific IO transform for some specific format. In case of Parquet, we could use Parquet.io to read files. Let's apply to the P collection, apply, and call Parquet.io. To produce builder to read Parquet files, we need to call few methods. It's read method and from method. Read method requires the schema as an argument, but it's not actual Beam schema. It's our schema, because Parquet.io implements with our schema. But likely, we have our utils what easily could convert Beam schema into our schema. And it requires Beam schema as argument. To from method, we need to pass file pattern, what will be passed to Google Cloud Storage. And in this example, we have specific parameter to get file pattern. So, in general, to read packets, that's all. Let's take a look what type return as Parquet.io. So, let's pick collection of generic records, but we need a collection of raw. And our next step, convert generic records into Beam raw. Easiest way to convert one type to different type in Beam, it's using map elements into with specific type descriptor. Let's use it. Just apply map elements into to Parquet records. Yes, and specify type descriptor of raw class because we need raw as a output type. So, one more thing, what you need to specify using map elements into, it's via, and you need to pass serializable function to via method. Likely, it also contains in our utils, and we can call methods from our utils to get necessary function. Our utils get generic records to raw function, and it requires Beam schema. So that's it. Last thing what we need to do is coder specifying, because when we transform one type to different type in Beam, it requires to specify coder. Set coder, raw coder of Beam schema. Yes, that's it. I think that's all, and we can return the collection of raw and use it in switch case statement in Parquet value. And you may see we also have simple function for any different supported formats. And we don't need to change anything else in our pipeline because our main business logic implemented with Beam rows. Before we start build template, let me share one more difference between pipeline and template. That's metadata file. You could implement JSON file, name it metadata, and specify here description of your template. There is name, description, and list of parameters. For each parameters, you could specify name, label, help text, what helps user to pass right values in the specific parameters. Param time, it could be primitive or Google provided types. Is optional flag, it could be true or false for optional and required parameters, and regular expression. You can add your own validations to the specific parameter. In this case, we need to add new value, Parquet here, and let's add it also in help text. So I think we're ready to build pipeline to the data flow template. I prepared build script, and there are only 2 commands. Let's run it because it will take a bit time. And while it's running, let's discuss about building commands. First, you need to package your Java classes into the single jar, included all dependencies, using Maven or Gradle, for example. Next, you need to build data flow template using Google Cloud command line tool. You need to call gcloud dataflow flex template build and pass here few necessary parameters. First, you need to pass path to Google Cloud Storage, where Google Cloud Command Line tool will store JSON file with manifest of template. That includes metadata file with list of parameters and link to Docker image in Google Cloud Registry. You also need to specify path to the specific Google Cloud Registry image and SDK language. In this case, it will be Java, and you can specify Python, for example. And next one, parameters. Let's base image for the Flex template. You could use Google provided images or build your own image based on Google provided images. And last three parameters, that's just metadata file, jar file, what we built using Maven, and environment variable with link to main class of template. So while it's building, let's review project structure and take a look how you can organize your template code. In this example, we split all our Java classes by separate packages based on his responsibilities. First package, options. This package contains all logic around the pipeline parameters and options. Second one, templates. Templates contains main class of the template. Third one, transforms. Transforms contains all transforms, all necessary transforms, what we need to apply to P collections. And IO subpackage contains IO transforms, our own implemented transforms to convert source format to the beam row and beam row to the destination format. Last package, utils. We contained here all supported classes, for example, to work with schema, to parse JSON schema, or building CSV records. So let's take a look on build command. Yes, and it's close to get builded, and yes, that's done. So we're ready to run our template, and there are few ways to run template. It's using Google Cloud Command Line tool, using REST call with any REST clients, and using Google Cloud Web Console to run template manually. In this demonstration, we will go through the two approaches to run template. It's a Google Cloud Command Line tool. We run data flow job using command line tool, and we will go to the Google Cloud Console to run it manually. There are just Google Cloud data flow flex template run command with passing template location, region, and list of parameters. We will go through those parameters in Cloud Console, and let's just run it from terminal. Yes, job is running, and go to the Web Console. So to run job manually, you need to go to the data flow service in Google Cloud Platform. As you may see, our job from command line is queued and it will be running. To run new job using Google Cloud Console, you need to click Create Job from template. You need to pass name, choose the region, choose custom template in this Dropbox. You need to go for the Google Cloud Storage and choose JSON file what was stored with Google Cloud Command Line tool. And all necessary parameters fields will be generated automatically based on metadata file. So to save our time, I already passed all necessary parameters in necessary fields. And let's pass to Parquet schema, what we showed before, We need to specify parameter. Let me demonstrate how validation from regular expression works. Let's just specify XML, and we have error message. We need to specify Parquet, of course. And we need to specify file pattern to input files. I want to read any Parquet files from Google Cloud Storage. Also, we need to specify tokenization URI and batch size for our stateful processing. We will buffer 10 elements before we send it into third-party REST service. We need to specify output path and output format, let it be CSV. So I think we're ready to run job. And while it's running, it needs a bit time to provide some resources. Let's take a look on the previous job, what is running state. As you may see, we have two steps, read Parquet, and next step, map elements. We didn't name it for some specific name, and it just map elements. Read Parquet, it's our own implemented Parquet reading using Parquet.io. And map elements, it's transformation from generic records to Beam row using map elements into and specific function. Next two steps, it's tokenization steps. And last two steps, it's conversion Beam row to CSV format and write CSV to Google Cloud Storage. So that's all from live demo site, and let's go back to the presentation. Recapping the demo, we took a look at the approach to organize template code structure. We saw what is the metadata file and how you can describe template parameters and add some validations. We discussed schemas and mentioned it at the approaches, how it can be represented in JSON format. We've implemented reading functionality from Parquet files and transformed Parquet generic records to Beam row. And at the end, we built and ran template in Google Cloud Platform. It was really easy. To find this template and search for more use cases, you can take a look to the GitHub repository. There are a lot of implemented Google provided and community templates that can be helpful. To share your own template with community, you might contribute them to the Dataflow templates repository. It's easy to get started with these contributions. Just fork repository to develop template and pipeline, following the style guides and best practices, sign contributor license agreement, submit pull request to merge. It will go through the code review to get merged into the repository. Let's summarize our session. What we learned today. We discussed Dataflow templates, difference between pipeline and template, and how Flex templates package pipelines into containers for easier sharing and running. We went through an example user scenario for Dataflow templates and how to implement a scalable architecture for interacting with third-party REST service using Beam. We dive deep into stateful processing, use cases, and recommendations for stateful Dufan and group into batches. We learned how Beam row can be used for data representation and demonstrated benefits of Beam schema and API and row as a common abstraction. Finally, we looked at how to get started contributing templates to open source community. Thank you for joining us in Dataflow templates session. We are happy to answer of any your question.
Thank you very much, everyone. This was like did you practice for this session? You were very coordinating when each one started and the next one followed. So I hope I'm sure this will be a very good session for everyone. Yes, we have some questions for you. First is question. Let me see. For Arthur. Well, it is he is tagging Arthur.
Yes, it's me.
It seems provide example is not working.
Yeah.
He's sharing a screenshot at the Slack, so you may wanna go to the Slack and answer the question there.
I can answer there, or can just say a couple of words here.
Yeah.
So basically the example that I showed is with the code snippets. They are quite generic. Yeah, so it's not the totally working code. Yeah, but that's true. It misses. There's a missing key value. Like typing. Yeah, so these events, they should be wrapped with key values. Yeah, and everything works fine then.
Okay.
So yeah, that's actually the answer for this question.
Okay. And Pradeep is asking, is Beam Raw available for both Python and Java SDK?
Yeah, I think it's available for Java SDK, and as I know, for Python SDK, data frame API is roadmap in Beam and in implementing state. So, and it will operate with Beam Raw too.
Okay. And here's a question from Pierre. Does Beam Raw support schema evolution? For example, allow Raw 1 to have different schema than Raw 2? And does Beam Raw support sparse objects? Example, efficiently ignore all keys with null values.
So let's try to answer to this question. In Beam Raw schema API, we could produce different rows based on previous one. For example, you could implement transform, Beam transform, and implement some logic to convert first row to second row and inheritance any required fields, for example. And second question about null values.
Does Beam Raw support sparse objects?
Effective row, all case with null values. Oh, so let's think
I can catch this one.
Yeah.
As I understand this. So the thing is that you have to specify. So since Beam Raw has its own schema, you have to specify the field as nullable. So, and if the field is nullable, then yes, you may have these sparse objects, with null values. But if there is it is a required field, then you can't actually parse null, and it will argue. About efficiency, I don't think there are such optimizations. Yeah, but don't you know, Ilya, about handling nulls?
No, I don't know about it.
Yes,
so it seems like no, if we don't know this.
Yeah, I'll say no. Okay. If you figure out that did work, I mean, it does something with the null values, you can come back and let us know. Another question is, does Beam Raw also support different RDMS IO, like MySQL or Progress SQL?
So, I think to convert Beam Raw to the destination format, for example, to JDBC's prepared statement in Java to insert into MySQL or Postgres, you could use specific transform from Beam SDK. And I think it's not supported directly with MySQL and PostgreSQL because it's Beam Raw abstraction for Beam SDK.
PostgreSQL, sorry, I misspelled that. And I have a question for Arthur. Is there a limit in size of what can be stored in states? full history? Example full history. If not, which current database is it possible to choose another database that will allow for it, like Bigtable or something else?
Yeah, that's a great question, actually. And yes, I can definitely say that yes, these states, they have limit. Well, Dataflow Runner actually uses Windmill database behind. Yeah, but it depends on Runner. Yeah. And of course, if you want to put their full history, it will blow up your memory and everything will fail. So please don't do this. Yeah, and you actually can replace Windmill with your own choice of database, but it takes a lot of pain to do this because actually you have to implement this in Runner yourself. So you have to dig deep into these implementations and make it work. So yeah, well, actually, I think Windmill, yes, and this already implemented solution is the best for this purposes.
Okay. Here is another question for Ilya. Is it possible to dynamically change row coder?
I think to change row coder, we need to apply set coder to P collection and change coder when we need. If we change schema, we need to change coder.
Okay. Let me see. Somebody looks to be typing a question. Yes, it's another question for Arthur. Is there a plan to have Windmill supporting bigger data size?
Well, honestly, I haven't asked people who work with developing like enhancing Windmill behind the scenes of Dataflow Runner. So yeah, I'm sorry, can't really answer this.
Yeah.
He's typing another question. I'm waiting a little bit. I think this is going to be our last session for today. Yes, and also, sorry? Yes, Alex.
Thank you. I wanted to mention that demo that Ilya performed today in the session is also available as a code lab on GitHub. So if anyone wants to, I know it was pretty fast to go through all the steps, and there's some setup needed to really get that environment for the demo. So we have that available in GitHub repo for Beam College Day 3 today, Dataflow templates.
Perfect, thank you. Well, thank you guys. There were just thank you messages, no more questions. But anyway, if you still have questions, I'm sure that Arthur, Alex, and Ilya will be around at the Slack. Keep answering, and I think you will have more sessions, right? During Beam College.
This is only session, but we'll be in Slack channel, and we have a question to follow up there as well.
Perfect. Well, thank you all.
Thank you, Beam community. Thank you, Mara, for having us here today.
Yeah, thank you very much. It's been a pleasure. Yeah.
Thank you. Bye-bye.
Thank you. Bye-bye.
Thank you. Bye-bye.
Bye-bye.